So good morning. Yes, I'm semi-retired, which means I'm busier than ever these days. But I spent 10,001 days at Intel, which is a little over 27 years. And before you go off saying that you'll never work anywhere 27 years, just give it a try sometime. I thought I'd work for Intel for a few years, but I had the good fortune to work on a lot of HPC systems. The first system I worked on, our tagline was building blocks for gigaflops. If you had enough of our chips, you could get to a whole gigaflop. And then I got to see us pass teraflops and go up to petaflops. And during that entire time, I always stayed very close to the metal. I'm very fascinated with computer architecture, with the software that lays on top of it. I worked a lot with compilers and performance tools. And I've literally worked on thousands of different applications trying to figure out why they weren't going quite as fast as we thought they should. So I thought I'd kick off our day today talking a little bit about how I think about performance tuning and try to boil it down to some simple things, give you some ideas of how to think about performance tuning. And the title of the talk kind of sums up what I'm going to say. To me, when you're doing performance tuning, you've got to get yourself set up to be surprised. And by that I mean you actually need to know what you expect your application to be doing. And I'll talk a little bit about that and about something called the roofline model that there was a nice paper from Berkeley on, and that Intel's implemented some things in tools to help do. But I think it was a good description to me of what I thought I had been doing for decades, drawing little graphs out on the back of envelopes and so forth. So share a little bit about that. So anyways, I might as well start off and tell you what my talk's going to be. So simply put, I'm going to talk about three different things. I'm going to mix them together. One is having expectation. Another is validating your expectations. And finally, the concept that you should have a methodology to the order that you do things in. And these three things, I think, sum up what all the different random things I'll talk about during the talk in different orders. I won't necessarily follow this in exact order, but these are the three key things to me in performance tuning. One is that when you're working with an application that you actually have expectations. The other is you try to validate those expectations. Another is you're following a methodology. Now, hopefully not giving away any desperate Microsoft secrets, but one of the projects I worked on that was not an HPC project is I worked on the very first Xbox. And we provided the vTune tool to Microsoft when nobody knew that an Xbox was coming. Microsoft was working on it in their secret labs up in Redmond. And we shipped them a copy of vTune, and they could finally run it on this platform. And we got a call a little later in the week, and they said, you know, we almost called you yesterday and told you vTune was broken. Because vTune told us that 25% of the time on the Xbox platform was taken up by this little tiny graphics driver. And of course, this is a highly efficient graphics driver. It would never take 25% of the time. That has to be in the game. They said, but we looked at it a little bit more, trying to figure out what mistake vTune was making. And then, well, we found a little lock that wasn't doing what it was supposed to do. And we really were taking 25%. And they said, we fixed that little thing, and now vTune tells us we're only taking a couple of percent in the driver. And I said, OK. So you know, the good news was they had this expectation that that was totally absurd. Of course, they did what a lot of people do, you know, right away, blame the tools, blame the computer, something's broken. But that's OK. I do that too. I get seriously worried, is it really plugged in, even though I'm debugging a program on a running machine. So but that expectation, I can't overemphasize how important that is, that you have a model in your mind. And I'll give you some different ideas of how to develop that, because sometimes, you know, actually, most of the time in your life, you're probably going to be working in code that you didn't write from the bottom up yourself. And so you may even have a challenge of figuring out what to expect. And I'll be able to talk a little about that. So, well, first of all, just to make sure people are awake, had enough coffee, can anybody tell me, I hope in the last week you've at least touched on this, can someone tell me real quick what a cache is? Everybody's going to be really nervous. This is great. None of you know what a cache is. That's kind of embarrassing after a week, don't you think? Local storage, I'll accept that. So, it's, yes, to date me too excessively, that, the earliest microprocessors I worked on didn't have caches. Nowadays, the caches are so complex and there's so many layers of them that can give you a headache. At one point, they were actually a novel idea, because it used to be that computers would decide that they wanted some memory and they'd go contact the memory and bring it in. But as we made processors faster and faster, caches become a storage somewhere between the memory and the processor to hold data locally. And the idea is that it should accelerate you. And the idea initially was that the caches would just be invisible and they would mysteriously accelerate you. But of course, performance fiends like ourselves start to realize that if we organize a program a certain way, the cache will behave more efficiently for us, and other ways it won't. So we start getting worried about caches. But anyways, I'll come back to caches in a little bit. But for now, caches sit between the memory and the processor. There may be multiple layers of caches, so there may be, in that scheme of things, there may be different cache layers. But those become important only because we're going after performance. Supposedly, the hardware just magically handles the caches for us. The only reason we get concerned about caches is we realize if we rearrange our program, it'll get more efficient. Now, why do we care about efficiency so much? Well, there was this guy named Amdahl, and he created this Amdahl's law, which you'll learn to curse after a while. But it's if I had 10,000 cores, but my program's only 50% parallel, I don't get very great speedups. I suppose, if I was really efficient, I would have labeled this axis speedups and that axis cores. But you've got 50% parallelism. Even 80% doesn't give us great speedups, and 90 and 95 and 99. You've probably seen curves like this before. If you haven't, and you start drawing them out, you realize it's not worth a lot. In any of these diagrams I've drawn, it's not worth a lot to get more than, good luck with 100%, but it's not worth getting just 99% parallelism. In fact, if we're only 10% efficient, you see most of these curves are below 10% efficiency. In fact, if you want to make sure you don't get an Energy Star certification, 1% efficiency, you can see that the majority of lines here, until I get to 99% parallelism, don't even give me a 1% efficiency in the machine. So, the whole reason we're talking about performance analysis and all these techniques today is really comes down to Amdahl's law. If you want to sit on top of one of these large machines with a lot of cores, you really need to be able to get all the performance kinks worked out in your application. For instance, if I offered you 10,000 cores, but I had this crazy idea that I only wanted you to have 50% efficiency, if you're only 95% parallel, I can give you 21 cores. When I give you 22, you won't be 50% efficient. These numbers are kind of staggering, and I do know some compute centers actually make users, and your mileage varies different compute centers around the country, around the world, but some will insist that you demonstrate your program scales a lot before they unleash you on 1,000 or 10,000 cores. And this is really why, because if your program's got 9% or 5% serial, which I'm sure no one in this class would ever have that problem, going beyond 21 cores doesn't do you much good. So, and even if we want to only be 10% efficient on the machine, 95% parallelism, still 181 cores, we better stop there. Anyway, some rough ideas. These numbers are very frustrating. Now, last week I was at SIGGRAPH, and I was giving a presentation with some friends from the visual effects industry. That'd be Pixar and DreamWorks Animation, side effects, different companies that I've worked with and put a book out together back in 2014 on multi-threading for visual effects. Now, these guys are very different than HPC. They are enamored with workstations that are maybe have 24, 30, 32 cores on them. That's where their animators work. And then they have render farms. And anyways, one of my friends, presenters from Pixar, he threw up this, Florian, he threw up this diagram. And what this is, and you'll have diagrams like this for your applications, but what they're doing is they're handling a very diverse set of animations. There's different parts of the characters that are being animated, so forth, and they want to do, the big deal in visual effects these days is to try to do real-time animation. So this is shows when the different processors are busy. And if you look at that, that looks pretty good. But then you could ask, is it underutilized? Well, here's his performance graph, trying to take advantage of a machine with, I think this one had 18 cores, if I remember right, 16 or 18 cores. A 3.3x speed up, he's actually pretty happy with that on 18 cores. But he thought, wow, I could do better. Now, when he looked at his thing and asked the question, is this underutilized? He did a novel thing. He started staring at it this way. And I liked this diagram. And I said, gee, I'm giving a talk next week. Can I show this diagram? Because it gave me a real good idea of the sort of things. I'd never seen anyone present it and show it on a slide real nice, what I'd be looking for. It's like, are there bands here where my parallelism goes down, where it's not strictly serial, but the level of parallelism in the places that aren't shaded is pretty low. So rough thing, it looked like we're about 20% underutilized. So, you know, lo and behold, if you were to plot Amdahl's law at 80% efficiency, the application's not doing bad. So this confirms, this is an example of understanding what parallelism or what you expect out of your program. Suddenly, if our program's only 80% parallel, the results aren't surprising. And we know that our number one issue probably is the level of parallelism. So we need to focus on how can we stamp out these non-parallel parts. So after a little bit more work, which was discussed in this class, with what sort of things they were doing different in the rigging by optimizing the rigging, the parallelism went up to about 85%. You can still see there are some bands over time where the parallelism isn't that great, but the program suddenly leaps to 4.3x performance, which is tracking, again, Amdahl's law of 85% efficiency very closely. Now, hopefully your curves will be much higher, that you'll be looking at 99 and several more nines at least in parallelism when you're going on big machines. But the principle's the same, paying attention to how close am I getting to some maximum, to some roofline, I'll call it later, where I've drawn a line other than this ideal. Oh, I didn't explain. You may notice this ideal line here is not a straight line with the number of processors. And that was an interesting note as well. On workstations, they are not, the thermal envelope for a workstation generally doesn't allow all cores to be busy full out. It will throttle. Now, you'll run into this even on HPC machines under some circumstances, but in general, HPC machines try to make sure that the throttling is minimized for programs that are doing all out. But workstations tend to say, hey, almost nobody ever gets me fully busy, so I'll design it so that I'll slow down if someone tries to get me completely busy. And it means that the curve for the maximum they can obtain is still not a straight line. And he had plotted that out as the best case and used that as a head. So the punchline in the talk was he still had more headroom, and he got some laughs in the class we were teaching because he said, you might have been expecting I'd show something really wonderful. He says, maybe next year. Anyways, I always say what I'm looking for is something unexpected, and that goes back to I do spend time before I jump into a tool of any sort trying to write down on paper what my expectations are. Because, you know, it's kind of like going in a dark cave, and shining a flashlight in, you do need to go in, poke around, and look. Now, I'm sure you write perfect programs the first time like I do, so maybe you don't think you need to go in and look around, but it's kind of fun. And who knows, you might find a bug from someone else. But you get in this cave and your flashlight around. That's what I always think, that tools like vTune or Tau, all these different tools that you can get, and I generally try to make sure I have all of them installed on my machine because they all give me a little different look in a system. And I'm looking for confirmation that things work the way I expected, and I'm looking for surprises. And this is, and your expertise will grow as you look around, by the way. You'll start figuring out. So, it's very funny when you get to an expert with any tool and you sit down next to them, and the next thing you know, they're hitting keystrokes so fast that, you want to take the keyboard away from them and have them tell you how to do it because you can't tell what they're doing. And it's because once you get used to these different tools, it's like, oh, I know what I want. Click, 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 click down, and you look at this one thing. I want to see if this is working. So that really grows with experience. I can't overemphasize how important it is to make sure you carve out time to go look. Now, methodology-wise. So methodology, it's important not to zoom to the wrong level of tuning too fast. Now you probably won't run into this with HPC as much, but let's see, go back. If you've got the wrong BIOS parameter set, or if you've got a slow disk drive, it probably doesn't help to go tune every little step of SSE and down in the weeds if you haven't taken care of the high-level things. But most of us go to the application tuning. Most of us are blessed. We'll be running on a machine where someone else has tried to tune the system, set the BIOS the correct way, pick the right disk drives. So for most of us in HPC, we'll spend time on what I call the application tuning area. And most of the time, the concept of a hotspot is important. I want to go figure out where most of my time is being spent. Especially if your program is highly parallel, or you want it to be highly parallel, you want to go find where almost all the work is going on. So this concept of finding a hotspot is enormously critical and constant throughout our work. So then, go find the tools that'll help you with that. And you'll see later, Larry Meadows is here from Intel, I know. That's why Scott called me Larry briefly, is, like Intel people are pretty much interchangeable. So Larry will talk more about vTune, I assume. Actually, I've not seen Larry's talk, but and he'll talk a lot about hotspots. I'm sure the Tau folks will be similarly showing you how to get hotspots. This is a pretty common concept. Now, you figure out your own granularity. Do you want to know it on a function, a module level, whatever? It gets a little complicated if a function is a hotspot, but when you look back in the call graph, it's being called from 6 different places. HPC apps don't do that as much as some others do, but when that happens, you have to think carefully, and you may realize that a function is being less efficient when it's called from routine A than it is when it's called from routine B. So the changes may be in A or B, even though the function is 99.99% of your runtime. So these tools, the ability to show you the hierarchy, show you how they're being called, what type of parameters, because perhaps one of the functions calling you passed you a misaligned data thing. So, it's a bit of poking around in the dark is a funny thing to do. You find a function that's not working real well, you can stare at that function all day long, or you may stare at the functions that are calling it and the tree and the data that's being passed. But you get to figure out your granularity, poke around. The tools, I always think is just illuminating. They show you things. Of course, you see them, you see this nice little graph and go, so what? You see these graphs, so what? So a lot of the tools folks are going to show you what their tools can do. Again, I think the best thing you can do to take good advantage of them is have a concept of what you're expecting, so that as you use the tools to illuminate things, you're surprised if you see something, if you didn't expect a giant bat in the cave. Now you can look at other things too. Characteristics of the program, like how well threaded it is it memory bound, is it CPU bound, these things. Again, having an expectation helps a lot. If you're using a KNL machine, have a back-of-the-envelope calculation of how many flops were you expecting, or how much memory bandwidth were you expecting? Did you expect a lean on it? What's your parallelism level? What's your wall clock time like? How is your program behaving compared to what you want? It's challenging when I got to work, like I said, with thousands of different applications over the years. And sometimes I'd sit down with somebody and they'd say, my application's running in 5 seconds, I want it to go faster. And I'd say, well, how fast do you think it can go? I don't know. It's like, okay, well, that would be then the first thing I do. It's, well, let's try to figure out how many computations you really need to do. And I'd go back to the basic math. Because if you go count how many flops it's doing, or how many floating point operations it's doing, not floating point operations a second, if it's doing 1 billion calculations, you can ask the question, does it need to do 1 billion? Maybe the compiler didn't optimize well. Maybe I wrote it wrong. Maybe if I can do it with 500,000 or 500 million calculations, it might run twice as fast. So I need to, just not take for granted the fact that it's doing 1 billion calculations, that it has to do that. So doing a little back of the envelope, knowing what I'm expecting is critical. And how parallel it is. This is some stuff that some of the Intel tools can show you like this. This is very similar to the diagrams I was showing you from the SIGGRAPH talk, showing on a workstation parallelism. I find these very helpful, the time-wise diagrams. They show you what's going on. You can even do that with MPI as well. Well, you can look at memory bandwidth. I think the next one is MPI. This is an MPI diagram from one of the Intel tools, the thread checker. The red is bad, and you can see long times here for synchronization is what this shows. It shows that the top node is busy almost all the time, but most of the other nodes are waiting. And so in this particular diagram, if your application looked like this, there's a lot of computational power available on this machine that's being completely not used. Very similar to the SIGGRAPH talk, except I think this is much worse than 20%, this particular diagram. So, you find the hot spots, you look at compiler optimizations, you look at things, you're going to see the tools are going to show you a lot of different things you can poke at, and then you need to figure out what to do with it. So back to, checking on how the coffee is doing. So no one knew what a cache was, but I taught you. I'm very profoundly honored to have taught you what a cache is. So anybody tell me what a cache miss is, given your newfound knowledge? Yes.
You want to get the cache, it's not there, you have to go.
Exactly. So the processor has got this cache sitting between it and memory, and it consults with the cache and says, hey, I want this data. And the cache says, sorry, I don't have it. And so we have to go to memory. Now, a cache miss means that the cache isn't able to return it to the processor very quickly. Instead, the system has to go request it from memory, which is slow. The whole purpose of having the cache there is you hope that the data is already there. But it has to come to the cache sometime, so it's not there. So a cache miss is that. Now, the really big question I've been working up to is, so what happens if we reduce the number of cache misses in a program? If I have a program that I used vTune on and it told me I had 400 million cache misses in a particular function, and I go carefully optimize it and I get it down to 200 million cache misses, what happens to the performance? What guarantees are there for me? Depends on the application. Okay, well, maybe they were teaching you something last week. Yeah, this is one of the things that always is very frustrating. With the modern architectures, and as sophisticated as they are, caches were put in there to try to be automatic, and then we started programming to them. And then there's all sorts of other things going on, out-of-order execution. Processors used to stall. If they couldn't get their inputs, they would stall. Well, instructions still stall, but a processor will actually perform multiple instructions at a time. And so what? These instructions are stalled, but these others can move forward. You can actually reduce the number of cache misses in a program enormously and have absolutely nothing happen to your performance. So this is really something that'll drive you crazy. So very interesting. We would have these discussions with the architects at Intel that what we really wanted was to know when the processor was stalling and why. And Intel about probably 7, 8 years ago started introducing some of the counters. They call it stall accounting in the Intel documentation, at least some of the Intel documentation. And you'll go to vTune, and there'll be these mysterious counters, and some of them will say stalls due to. So you can have stalls due to cache line or cache misses. And what happens is if an instruction requests memory and it requests it from the cache, and the cache has to fetch it from memory, and somewhere along the line, the processor doesn't execute as many instructions per second or per clock as is possible, every one of those instructions that's waiting for data will tick up a counter saying, we're stalling because stuff hasn't come back from memory fast enough because of a cache miss. And if you actually count stalls due to cache misses, wow, if you can make that number go down, your program will almost always get faster. In fact, I think probably always will get faster. That's incredible. So it's yet another thing to learn about these tools is what are they really telling you? And yeah, I've more than a few times had people very frustrated they got their cache misses down, which they were really sure would help the performance of their program, and it didn't. Now, flops, usually if you reduce the number of calculations in a program, usually that'll reduce your performance, but not always either. You can make perturbations on that. So looking for, keep in mind what you're really trying to change. You're trying to make the program run faster. Can you measure that directly? Now, this performance monitoring unit that are in virtually every processor and even things beyond processors these days have counters in them, and they count things. The challenge is figuring out which ones are useful. Also, it's useful to know whether they're doing a statistical sampling or whether they're actually counting. And a lot of tools give you both capabilities. If you're actually counting every thing that's happening, you can slow down a program a lot more. If you're doing a statistical sampling, you have to understand it's statistical, and it may vary a little. It may not be a precise count. So if you look at a function and you count exactly how many flops there should be, but you're doing a statistical count in your tool, the tool may not match your number exactly. So you need to look at that. But I think the number one thing for me in counters recently, and I think anybody that does a lot of performance tuning on Intel hardware will tell you, they look for these two things. One is the stall accounting. They try to use counters that go after stall conditions. And the other is precise events, where the tool will point you to the correct instruction. And some things are the processor can only keep track of at a high level for you, the calculations, and it doesn't, if you were to stop it on an instruction that claimed to do something, it may point to an odd instruction. It's really weird to have a cache miss on an instruction that's not doing a memory access. And a lot of counters do that because it didn't think it was that important to be able to point to the correct instruction. So there are some counters that'll use this strange little word that they're precise. You would think they'd all be precise, but not. And so if you start zooming in, don't be surprised when the tool points to a floating point operation, tells you caused a memory access, and you look at it and it's using all registers if it's not precise. That usually doesn't matter as much. The stall accounting tends to be the big deal, I think. So there's lots of different counters you can choose from. You can choose whether you're actually doing the counts or you're doing a statistical or a metric-oriented thing. The other thing is most processors have multiple counters on them. So there's not usually a counter of flops per cache miss or whatever bandwidth things. There's usually not one counter that does that, but the tools often have fake counters. They'll say, oh, do you want to count this? And the next thing you know, that takes 3 counters out of the machine. Maybe the machine has 8 or 16 counters it can run at a time, or 6. And suddenly you ask for one metric and it takes up 3 of them, and it's because it's actually counting 3 things and then doing some math for you. But that can be incredibly useful, and then looking at all the different counts. So you'll get some more. You'll get inundated today with what tools can show you. And I'll say, look, have a methodology. Are you looking for hot spots? Do you have expectations? Are you verifying them? Don't let the tools wag you. Don't let someone with a tool tell you, you listen to them, see if it's that, see if that's the right methodology for you, but have an idea what you're trying to do. And don't skip this having an expectation. Now, roofline. This got to be, there's a paper by Berkeley, and I think I've put a URL here, a tiny URL, ATP ESC-roofline. I wrote a little article a few months ago about the roofline stuff. I've written different blogs over time pointing to this capability, and that the blog does have a pointer to the original Berkeley paper, which the idea is, how do you visualize this? And it's funny because my entire career, I've always done this myself. I learned it from others. When you sit down to do performance, you start drawing little graphs, and they might look something like this. I might have, how many flops per bandwidth am I trying to accomplish? What are the limits of the machine? How close am I getting? Some of the diagrams I showed you earlier fit that characteristic. I might have fit Amdahl's law to it. I might have fit the bandwidth of the machine, the flops. The question is, do you have a model like that? Roughly, for a while, the intensity or flops per byte, you'll be memory bandwidth limited for a while unless your application has a lot of computation per byte. When you hit that, you hit a compute bound limit. It does not help to optimize your flops when your memory bandwidth, and it does not help to optimize your memory accesses when you're compute bound. And wow, you can go over here and optimize the daylights out of your cache misses and so forth and see no performance change. So knowing where your application is operating. And there's not just one limit. If you fit in L1 cache, you'll have higher bandwidth capabilities. If your data is in L3, your capabilities less. If you're able to hit FMAs, you have a balance between multiplies and adds, you can get a higher computational limit, whereas if your program's only doing scalar adds, not even vector ones, this is the most you can expect. Now, you don't have to pass judgment on your application. If your application absolutely cannot be vectorized, you're going to hit this limit. And all the optimization in the world on your program won't help you if that characteristic of your program remains constant. And that's incredibly valuable to understand. If you get over here on your performance graph and you're hitting this limit, knowing you've actually hit the limit of the machine is valuable. Now, of course, you may want to figure out how to get your program to vectorize, rearrange data, whatever. That's when that optimization becomes valuable. So these sketches on the back of envelopes, I've seen forever. And then, it's cool when somebody sits down and writes a paper and says, I've got a formal idea of how to think about this. And they called it a roofline model. A roofline being that these somehow resemble the top of a building, a roofline, and you can't exceed that. When you're inside the house, you float up to the roof, and you can't float beyond unless you poke a hole in the roof. So this is the keys to me are, why am I here? Why is my performance what it is, and where do I want to go? And why aren't you on a higher ceiling? Again, vectorization would let you go to a higher ceiling. That'd be great. And what do you have to do to reach it? These are key questions. Now, breaking news. There are things tools won't tell you. And you can sit beating your brains out with roofline models and so forth. And so in one of the books I worked on, we were working with Stephen Hawkins' group, and they drew this beautiful diagram here. This was on a KNC machine, but they start off with a Xeon, and they keep improving it to get it faster. Finally, they start using a Xeon Phi coprocessor, which is the gray line, and they're showing the speedups. And this number here is the ratio. At this point, the Xeon Phi is only doing 43% as well as the Xeon. And so they make these different optimizations. And everyone I show the diagram to says, oh my gosh, what is that bar? That's the jump. I want to know what that is. because they carefully detailed step by step what they were doing to change their program. We show the code. These guys were very gracious. There's a fun chapter to work on with them, showing the different steps of optimization. And by the way, shameless plug for some books that I've worked on, but the books I probably love the most are the ones we call the Pearls books, from the perspective that I get to work with these amazing people from around the world working on different codes who actually showed how they thought about optimization step by step. And there's different codes from different fields, but you start to see that when you break it down, what people are doing, well, it may happen to be rocket science, but the code itself I wouldn't describe as rocket science. It's kind of plodding along, looking at things, understanding it. Well, these guys, this is the documentation they have here for what they did at each step of the way. But if you look at step 7, they changed their numerical integration routine. They realized that the routine they were using in MKL was computing a very nice, it was doing a very nice integrator triangulation. They didn't need it to be that precise. They didn't need it to be as nice and as well conditioned as MKL was doing. MKL was doing it as fast as possible, but they were asking it to do more work than they needed. So they went back to some simple math and wrote their own routine to do it to the level they needed, and it resulted in a 10x improvement in the program. The overall application jumped 10x by changing this one routine. They could have optimized it all day long. They could have stared at it with VTune. They could have tweaked it. They could have used compiler options. They were never getting 10x out of this. They rewrote it. Don't forget to pay attention to the fact that sometimes you're not using the most efficient algorithm. Yes, again, if you're doing 1 billion floating point operations and you can get away with 500 million to get the same math done or the same science done, do it. And some applications are more tolerant to changes in the actual mathematical answers. Some are very reliant on them. You have to understand your application. But there isn't any tool you're going to see that's going to point to a routine and say, oh, rewrite this algorithm. Or if it does, I'd be very skeptical. How on earth? Now, maybe with AI, we'll figure that out one day. But this is really on us. So don't, what's your expectation? And again, you can say, well, why? And hotspots, which I mentioned, which are really important concepts, if you're staring at a hotspot, don't forget to ask, is there a different way to do this computation? And then the granularity comes in, too, because if you're calling a routine and it has 3 parameters, and one of the parameters is always 10, you might think, gee, if I wrote a version of that routine that had that parameter, if I knew that number was coming in as a 10, can I rewrite the algorithm and call a version of it that's more efficient? You never know. This is why sometimes it's just nice if you can take the time to wander around with these tools, looking at your code, poking at it, a combination of debugger, looking at the values of things, and performance tools telling you where the time is being spent, and kind of get to know your code and start to notice that's kind of odd. There are things that in everyday life you would notice, like if we go to a buffet later and there's 2 sides to the buffet, but everybody keeps lining up on one side and there's only an occasional person using the other side. When you see that in real life, you say, wow, that's not efficient. Sometimes you just don't see these things in your application. So you spend time in the tools looking around, poking your flashlight at things. Don't be afraid to look at things you're really sure you know how they work. Because if you're surprised and go, wait, that's not the way I designed that part of the code, those are worth a lot. So anyways, don't forget your algorithms. And with that, I've got a little time for questions. I'm happy to talk about performance. I've had a rich career, so I'll try to field questions of anything that might be of interest to you. And I hope this is a useful outline for the day ahead for you, to really value those expectations. Don't just jump into the tools without some expectations. And then wander around in these tools you're going to see today with your application and see what surprises you. Surprises are priceless. next speaker is welcome to come get set up, and if there's no questions, we can start early, but wow, they need stronger coffee.
Could you talk about how you sort of start forming expectations on the application that you've seen before?
Yeah, that's a great question. How do I form expectations for an application? So yeah, I walk into a customer site. They say, I want this application to run faster. And I go, okay, let's slow down. Let's talk about what is your application? I always start with an algorithm question. It's like, what question are you, problem are you trying to solve? I guess that's always it's a great question. I always ultimately, what are you trying to compute? Because sometimes I find people running applications where they're computing 3 things, but they only want one of the answers. Those are good days. They don't happen often enough. But get a real good idea of that. And then the question is, how are you computing it? And I do always go down to, in an HPC app, I'm generally like, well, how many flops and how much memory do we think this needs? And in an ideal sense, it's like, okay, what's the minimum number of calculations? What's the minimum amount of memory I need to touch? Let me compute that. Let me compare that to what I think the machine's theoretically capable of and see how far off we are. If we're within 10 or 20%, I start to doubt that I'm going to have a good day. If we're off by 10x, I go, whoo, this is going to be a great day. Why are we off? If we're off by 10x, my mind quickly goes to memory layout. Memory layout these days, moving data around dominates machines. Now, this has actually changed a lot in my career. If you asked me this question 25 years ago, it's always flops, because memory was fast and the floating point was slow. But we've reversed that, and it's never going back. Compute is cheap. So yeah, I spend a lot of time worrying about memory. How efficiently is it being used? So I'm constantly trying to figure out for an algorithm in an application, what's the minimum memory I could envision it touching. Of course, there's realities in the application where you stream through the data multiple times or something, and you realize you're going to blow your caches out. You constantly worry, though, if I rearranged it, could I reduce it? But yeah, I definitely start by, that was the methodology part of it, start by trying to figure out, in the simplest possible terms, what are we trying to compute? What are we trying to get away with? And then it almost always goes down to memory these days. Some aspect of worrying about, are we shuffling memory around more than we should be? That's what optimization is these days to a large extent. And that includes moving it across MPI, of course. Anything you do to move data around costs you time that you're not computing anything.